So the previous problems talk about adding so many joules of heat energy, or how many joules of heat energy or calories of heat energy are going to be added. And the way this is done is with a calorimeter. So that is just a fancy name for an insulated container. And the reason the container is insulated is because you want to have all the heat being within the system that you're looking at and not have any heat lost to the surrounding air or bench or anything like that. Because then you can do calculations if you know that all the heat has remained in the system. So in this situation, you are mixing some hot metal and some cool water in an insulated container, and they both reach a final temperature of 29.6 degrees Celsius. So we have heat being lost by the metal, and we have heat being gained by the cool water. And since the heat is not being transferred to the outside air or bench or anything, the heat that's lost by the metal has to be equal to the heat that is gained by the water. So you'll notice that the temperature changes are not equal. We have a much bigger drop in temperature for the metal than we do a rise in temperature for the cool water. But the heat has to be equal. So here we have the heat lost by the metal being equal to the heat gained by the water. They're in opposite directions, so I put a negative in front of the Q of the metal, because they're opposite. They're equal in magnitude, but they're opposite in direction. And so another way that you often see this written is that the total heat change of the system is going to be zero because there's no heat being transferred to the surroundings. So the change in heat of the metal and the change in heat of the water added together are going to be zero because there's no extra left over to be transferred to the surroundings. So you can use either one of these equations. Let's go ahead and work with this one. The Q of the metal is the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal. And the Q of the water, the heat of the water, is the mass of the water times the specific heat of water times the temperature change of the water. And that's going to add up to 0. So here on this side in green, I'll rearrange this equation to solve for the specific heat of the metal, because that's what we are trying to find out. So this is what we are trying to solve for. I'll do that algebraically, and then I'll do it here where I put the numbers in first. So what I did here was, since these add together to give 0, I put that one was opposite in sign to the other. And then to get the specific heat capacity of the metal alone, I divided both sides by the mass of the metal and the change in temperature of the metal. Alright, so plugging in some numbers here, we have the mass of metal is 28.77 grams. The specific heat capacity of the metal, we are trying to find that. And the temperature change of the metal is negative 70.9 degrees Celsius. When we subtract the initial temperature from the final temperature, we get a drop of 70.9 degrees Celsius. And then the change in temperature for the water is a positive 7.8 degrees Celsius. So plugging in the values for the water, the mass is 56.35 grams. The specific heat capacity of water is 4.184 joules per gram degree Celsius, and the temperature change we just mentioned is a positive 7.8 degrees Celsius. These multiply together to give 1,839 joules. The grams cancel, the degrees Celsius cancel, and because of the 7.8, there's only 2 significant digits here. I'm just going to underline the 8. I'll keep a couple extra digits for now. And then for the metal, the 28.77 times negative 70.9 is negative 2,039.8 with just 3 significant digits, and the units are still grams degrees Celsius. And the specific heat I put over here, we still don't know that. And those added together equal 0. So I'm going to go ahead and move or subtract 1,839 joules from both sides. I'll put a little bit down here. So then when we isolate the specific heat capacity of the metal, the Cm, then we get negative 1,839 joules divided by negative 2,039.8 gram degrees Celsius, which comes out to be 0.90 joules per gram degrees Celsius when we go down to the 2 significant digits. As far as the identity of the metal, the closest one that's on the chart that's in your textbook is aluminum. So we'll put that as the identity. If you look at table 5.1, you'll see that the specific heat capacity of aluminum is pretty close. All right, so this next problem shows a chemical process, not just a metal becoming cooler. Sometimes when you dissolve certain things in water, the water warms up. Other times the water cools down. So there is an energy transfer involved with this process. And we are going to do a little bit of this in our thermochemistry lab in a few weeks. So since we are assuming that there is no heat lost to the surroundings, then that means the heat involved in dissolving this ammonium nitrate and the heat that's being transferred from the water adds up to 0. So the heat change of the water and the heat change of the process of dissolving add up to 0. The heat lost by one is the heat gained by the other. So the heat of dissolving, we'll just leave the way it is. The heat change that's happening to the water is equal to the mass of the water times the specific heat of water times the temperature change of the water. So the temperature change of our water is the final temperature minus the initial temperature, and so it is a drop of 4.7 degrees Celsius. And since we are only going one past the decimal, the temperature change is only 2 significant digits, even though the temperatures themselves had 3. And these multiply together to give negative 1,715 joules with only 2 significant digits because of our temperature change. So our heat involved in dissolving is 1,700 joules approximately. And it is a positive change. The dissolving absorbed energy from the water. That's why the water cooled down. So this is an endothermic process because it is absorbing energy. Let's go ahead and take this a little bit further and see what the enthalpy of dissolving would be. So let's see if we could figure out the enthalpy of this process. It's more of a physical change than a chemical change, but a mole of ammonium nitrate solid going to a mole of ammonium nitrate in solution. What is the enthalpy change associated with that? So if we write the reaction like this, it's assumed to be on a molar scale, but we did not do this on a molar scale. We did this on a 5.95 gram scale. So let's go ahead and get the molar mass of ammonium nitrate. So we want to know the energy change per mole. That's basically what the enthalpy is asking us. For a 1 molar scale, what would the enthalpy change be? And we know that it is about a positive 1,700 joule change for 5.95 grams. So we could have converted this to moles first, but we could just put this as grams and then do the conversion for the moles now. So it is 80.05 grams per mole. And when we do this, we come out with about 23,000 joules per mole. I rounded it down to 2 significant digits again. A lot of times these are expressed as kilojoules. So dissolving ammonium nitrate results in a positive change of about 23 kilojoules per mole, and this would be written next to the reaction as just a positive 23 kilojoules because it's already shown that it's 1 mole that is dissolving. So the enthalpy of this process is about 23 kilojoules, and it is endothermic. It's a positive enthalpy change. The last couple of calorimeter problems, we did not factor in any heat being absorbed by the calorimeter. You can do that, and then it makes your calculations even more accurate. And this is one of the things we're going to do in our calorimetry lab, or our thermochemistry lab. We are going to calculate the heat capacity of the calorimeter. And then we will use that heat capacity of the calorimeter, also known as the calorimeter constant, in subsequent calculations in order to make them more accurate. Alright, so we have 3 things that we're going to take a look at now. The hot water is losing some heat, the cold water is gaining some heat, and the calorimeter is also gaining some heat. But besides those changes, there's no change happening outside the system. That's what we are assuming. There's no heat being lost or being gained from the air or the lab bench. So all of these 3 are the system that we're talking about, and outside the system nothing is happening. So these all add up to 0. Alright, so the heat change of the hot water is the mass of the hot water times the specific heat of water times the temperature change of the hot water. I have some delta T's up here. The hot water went down by 55.2 degrees Celsius. The cold water and the calorimeter both went up by 15.7 degrees Celsius. So here we have the cold water, mass, specific heat, change in temperature. The calorimeter is just the heat capacity times the change in temperature. We don't have a mass of calorimeter to factor into this equation. This is not a specific heat capacity, it's just a heat capacity. So this is going to be joules per degree Celsius, not joules per gram degree Celsius when we solve for that. And all these added together equal 0. So since this is what we are trying to solve for, let's try to get it alone on one side of the equation. Alright, so I went ahead and subtracted the calorimeter constant times the change in temperature from both sides of the equation. So instead of a 0 over here, I now have negative calorimeter constant times change in temperature. So let's go ahead and divide both sides by a negative delta T of the calorimeter. So that'll cancel this negative and the delta T, this negative and delta T. So this will just be the calorimeter constant. Alright, so I went ahead and inserted in some of these numbers: the mass of the hot water, the specific heat capacity of water, the temperature change of the hot water, and then adding in the mass of the cool water, specific heat of water, temperature change of the cool water, all over a negative temperature change of the calorimeter. So these 3 terms for the hot water end up being negative 9,827.2 joules with 3 significant digits. The blue terms over here end up being a positive 4,803.2 joules with 3 significant digits. And then we have the temperature of still negative 15.7 degrees Celsius. So let's put this over here. When we add these two, in the numerator we get negative 5,024.0 joules over a negative 15.7 degrees Celsius, which ends up being 320 joules per degree Celsius with 3 significant digits. So that is the answer over here, 320 with a decimal point joules per degree Celsius is our calorimeter constant. Let's do a problem where we use the calorimeter constant as part of our calorimetry problem. So here's another one of those problems where we are figuring out the specific heat of a metal. Last time we did this, we just said that the metal and the water, the Q of the metal and the Q of the water added up to 0. This time we're also going to include the heat change that happens to the calorimeter itself. So let's expand each of these heat terms. The metal is the mass of the metal times the specific heat of the metal times the temperature change of the metal. The water is the mass times the specific heat times the temperature change of the water. And the calorimeter is the calorimeter constant times the temperature change of the calorimeter. The temperature change of the calorimeter and the temperature change of the water are the same. I calculated this over here to be a positive 4.2 degrees Celsius. The temperature change of the metal is a negative 72.3 degrees Celsius. So let's do both. Solve algebraically for the specific heat of metal, which is what we are trying to isolate on one side. And then we'll also start plugging in some numbers over here on this side. So algebraically on this side, what I did first was subtract this water heat term and the calorimeter heat term from both sides of the equation. That left me with the metal, mass of metal, specific heat of the metal, temperature change of the metal on one side, and negative mass, specific heat, temperature change of water plus calorimeter constant, temperature change of calorimeter on the other side as a negative. And then to get the specific heat of the metal alone, I had to divide both sides by the mass of the metal and temperature change of the metal. So you could plug in all of the values here at this point and solve for the specific heat of the metal. I have here plugging the numbers in before you isolate the specific heat of the metal on this side. I'm going to go ahead and multiply some of these numbers. So this grams times degrees Celsius comes out to be negative 1,874 with 3 significant digits. These three terms multiplied together give 627.3 joules with just 2 significant digits. And then the calorimeter constant times the 4.2 degrees Celsius gives 220.5 joules with just 2 significant digits. So when we add these together and then subtract them from both sides of the equation, we get negative 847.8 joules known to the tens place. Then we can divide both sides of the equation by negative 1,874.7 grams degrees Celsius. And then rounding down to 2 significant digits, we get the specific heat of the metal being 0.45 joules per gram degrees Celsius.